Today, we're going to tackle a really cool math secret. It's all about one of the trickiest prime numbers out there, 17. And trust me, there's a surprisingly simple shortcut to figuring it out. All right, let's just jump right in with a challenge, shall we? Look at this number, 39,508. Is it divisible by 17? I mean, just looking at it, there's no way to know, right? It's not obvious at all. So what are your options? Well, you could, do the whole long division thing with a pencil and paper. You'd get an answer eventually. But come on, that's a lot of work. Or, let's be real, you're probably just going to pull out your phone, pop open the calculator, and boom, instant answer. Super easy, sure, but where's the magic in that? It's not very satisfying, is it? Exactly. It's boring. Very boring. There's no fun, no elegance. But what if I told you there's a much more clever, a much more interesting way to solve this little puzzle? Well, that's exactly what we're going to do today.
Yeah, this seemingly tedious problem actually unlocks a really beautiful solution. It shows us something pretty amazing about how numbers secretly work together.
And that solution, that secret, is a neat little method I like to call the 5 by subtraction trick. It's a seriously powerful way to test for divisibility by 17, and you don't have to do any of that heavy lifting. And you know what? The process is so simple, it's beautiful. It's just 4 steps. First, you split the number up. Then, you do a quick calculation. If you need to, you just repeat the process. And finally, you check your answer. All you're doing is taking that last digit, multiplying it by 5, and then subtracting that result from the rest of the number. You just keep doing that until you get a number that's so small, you'll know instantly if it's divisible by 17 or not. Okay, talk is cheap. Let's actually see this thing in action. We'll start with a nice, simple 3-digit number to get the hang of it, 221. All right, step 1, we split it. The very last digit, that's our f, is just 1. And the rest of the number, we'll call that y, is 22. Easy enough, right? Okay, now for step 2, the calculation. We need to do y minus 5 times f. So for us, that's 22 minus 5 times 1. A little quick math in your head, and that gives you 17. And, well, is 17 divisible by 17? Yeah, of course it is. And that means our original number, 221, is also divisible by 17. See? No calculator, no long division. Pretty cool. All right, I know what you're thinking. That was a bit too easy. It was just one step. What happens with a bigger number, where you might have to repeat the process? Let's give it a shot with 1,234.
So we do the exact same thing. The last digit is 4, and the rest is 123. So we calculate 123 minus 5 times 4. Okay, so that's 123 minus 20, which gives us 103. Now, is 103 divisible by 17? Still kind of hard to tell just by looking. So what do? We just do it again. So now our new number to work with is 103. Last digit is 3, the rest is 10. So we run the rule, 10 minus 5 times 3. Well, that's 10 minus 15, which is negative 5. And is negative 5 divisible by 17? Nope, not even close. And since this final little number isn't a multiple of 17, that tells us our original number, 1234, isn't either. It's really that simple. So, okay, the trick clearly works. But why does it work? This isn't some kind of magic trick, it's pure mathematics. So let's pull back the curtain and look at the beautiful logic that makes this whole thing possible. The whole secret is something called modular arithmetic. And I know, that sounds super fancy and intimidating, but it's not. It's really just a cool way of talking about remainders. Think about a clock. If it's 10 o'clock, what time is it in 5 hours? It's 3 o'clock. You're working in mod 12. For our trick, we're just working on a different kind of clock, a clock of 17. Okay, now this right here, this is the whole proof. I know it looks a little intense, so let's just go through it slowly, line by line. First, you have to understand that any number, let's call it n, can be written as 10 times y plus f. Remember y and f? So for 221, it's just 10 times 22 plus 1. Makes sense. Our goal is to see if n is divisible by 17. Okay, now here's the clever bit. We're going to multiply everything by 12. And you're probably asking, why 12? Hold that thought, we're getting there. So on one side, we have 12 times n. But on the other side, something weird happens.
It becomes y plus 12 times f. The 10 just vanished from the y. How? That's the magic of our 17-hour clock, our modular arithmetic. The main thing to get right now is that we've changed our original problem into a new one. And if this new thing, y plus 12f, is divisible by 17, then our original number n has to be 2.
So, let's answer that question. Why 12? The entire proof hangs on this one amazing fact. 10 times 12 is 120. Now, if you divide 120 by 17, you get 7 with a remainder of 1. That single remainder of 1 is everything. In the language of modular arithmetic, we'd say 10 times 12 is congruent to 1 mod 17. All that means is that in this world of 17, multiplying by 12 is basically the undo button for multiplying by 10. They cancel each other out. And that's why the 10y in our proof just magically simplified to just y.
Okay, so back to the proof. We got it down to y plus 12 times f. Here comes the last little piece of the puzzle. Let's go back to that 17-hour clock. If you start at 0 and go forward 12 hours, where do you land? On 12. Now what if you start at 0 and go times backward 5 hours? You land at the exact same spot. So in this weird clock world, plus 12 and minus 5 are the same thing. And since subtracting 5 is way easier for our brains than adding 12, we can just swap it out. And poof, y plus 12f becomes y minus 5f. And there it is. That's where our trick comes from. That's the whole secret. So you see, it's not just some random party trick. It's really a beautiful example of how powerful and elegant this idea of modular arithmetic is. It just goes to show that if you stop looking at the whole number and just focus on the remainders, you can find these incredible hidden patterns and shortcuts.
And, speaking of 17, it turns out it's not just any old prime number. It's actually a pretty special number, with some amazing properties that show up in some really unexpected places. I mean, check this out. For literally 2,000 years, all the smartest mathematicians thought you could not draw a perfect 17-sided shape using just a compass and a straight edge. Impossible. Then along comes this 19-year-old kid, a genius named Carl Friedrich Gauss, and he proves them all wrong. It's incredible. Or how about this? If you want to tile a floor with a repeating pattern like wallpaper, there are exactly 17 ways to do it. Not 16, not 18, 17. And if you ever get bored, type 1 divided by 17 into a calculator. The decimal repeats, but it takes 16 digits before it starts over again. The longest possible cycle for a prime like this. It's just a number that's packed with surprises.
And really, that's the whole point. The numbers all around us, the ones we use every day, they're full of these hidden connections and secret lives. It just proves that there's always something amazing to discover if you just know how to look a little bit differently. Which really makes you wonder, doesn't it? What other numbers out there have secrets they're just waiting to tell?